The emergence of organized military medical examinations in the 1840s marked a foundational moment for clinical engineering in the United States, as the convergence of national expansion, religious reform movements like the Second Great Awakening, and the drive for physical standardization created the moral, institutional, and technical groundwork for a new class of medical professionals dedicated to integrating instruments and measurements into clinical care. This early intersection of moral duty, state power, and diagnostic innovation laid the ideological and structural roots of modern clinical engineering as both a technical and ethical enterprise. In the 1840s, the United States was in the midst of rapid territorial expansion driven by ideology of manifest destiny, the belief that Americans were divinely ordained to expand across the continent. This surge westward required the mobilization of large number of settlers, soldiers, and workers, creating new demands for infrastructure, governance, and public health systems. The federal government began to implement more organized systems of personal evaluation, particularly in the military, where physical readiness was essential. For the first time, standardized medical examinations became a practical necessity, not just for screening recruits, but for ensuring that the nation's human capital would sustain the pressures of conquest, colonization, and defense. This context laid the foundation for integrating medical tools and the measurement protocols in national life, serving as an early functional precursor to clinical engineering practices. The religious revivalism of the Second Great Awakening, which peaked in the first half of the 19th century, left a profound impact on American culture and institutional life. It promoted not only personal salvation, but also a broad sense of social responsibility, encouraging believers to pursue moral reforms such as abolitionism, temperance, and public welfare. One outgrowth of this moral movement was a heightened focus on the body as a sacred vessel, worthy of care, discipline, and medical attention. Religious communities became strong advocates for public hygiene, mental health, and the humane treatment of the sick and poor. This spiritual ethic translated into real world support for medical exams, support for hospitals and health missions. It created a cultural environment in which the emerging logic of medical instrumentation, examining, quantifying, and improving the human body, was not only accepted but sanctified. The 1940s also marked a turning point in the rise of scientific thinking and the quantification of human life. Across fields from economics to anthropology, American professionals began to adopt numerical methods to understand and manage social systems. In medicine, this shift manifested in the increasing use of diagnostics, instruments, and health metrics such as scales, height measures, urine tests, all of this to assess physical fitness and disease risk. This data driven approach enabled physicians to detect patterns and anomalies with greater precision, aligning healthcare with broader movements towards standardization and efficiency. These early efforts to measure and monitor the human body at scale contributed to the development of public health systems and ultimately to the clinical engineering discipline, which would later professionalize the maintenance, calibration, and ethical use of such technologies used in patient care. Clinical engineering is a specialized branch of biomedical engineering focused on the practical application of technology in healthcare settings. It involves the management, optimization, and safe integration of medical devices and systems to support patient care. Unlike design focused engineers, clinical engineers operate at the intersection of technology and clinical practice, ensuring that machines, from diagnostic imaging equipment to infusion pumps, function reliably and safely within real world hospital environments. Their work bridges the gap between complex machinery and the human lives it serves, making them essential stewards of modern healthcare's technical backbone. The responsibilities of clinical engineers are diverse and mission critical. They are charged with ensuring the safety and performance of medical devices, troubleshooting and preventing malfunctions that could jeopardize patient outcomes. They often collaborate with physicians and nurses to select appropriate equipment and integrate it into diagnostics and therapeutic workflows. In addition, they play a growing role in managing healthcare technology infrastructure, including electronic medical records, data connectivity, and cybersecurity. In all of these roles, clinical engineers serve as a translator between human needs and machine capabilities, ensuring that complex systems work seamlessly and ethically in the service of patient care. The origins of clinical engineering are not only technical, but deeply institutional and moral. In the mid 19th century, as the United States mobilized for expansion and reform, the body itself became a site of standardization, evaluated, measured, and improved upon through tools and protocols. Early physical exams in the military and the public health sectors demanded reliable instruments and systems to ensure fairness, safety, and efficiency. This growing need to manage and quantify human health laid the philosophical and operational groundwork for what would eventually become clinical engineering. Far from being a purely mechanical endeavor, the field emerged from a societal impulse to care for the body through structured, accountable, and increasingly technological means. The institution of organized military medical examinations in 1840s represented a pivotal shift in how the government assessed and maintained the health of its service members. For the first time, recruits were screened not merely by observation or reputation, but through a formalized system designed to evaluate their physical readiness for service. These exams introduced the idea that health could and should be measured objectively using standardized procedures. This approach marked a foundational moment in American medical history, not only shaping military readiness, but also signaling the beginning of medical practice as a systemized and technologically informed discipline. As the U.S. pursued territorial expansion and military campaigns during the 1840s, a physically capable population became a national imperative. Soldiers, settlers, and laborers were required to endure grueling physical demands, making a bodily health a matter of strategic importance. Military medicine stepped in as the gatekeeper of physical standards, determining who was fit to participate in nation building. This function pushed medicine toward greater rigor and accountability, leading to increased reliance on diagnostic tools and uniform assessment protocols. The military's need for fit bodies acted as a force to function for the evolution of systematic health evaluation, laying a structural foundation that clinical engineering would later formalize. In meeting the demands of military readiness, surgeons could no longer rely solely on clinical intuition or anecdotal judgment. Objective tools like height rods, weight scales, and urinalysis kits became essential components of medical exams, enabling repeatable and defensible assessments. These tools introduced a new paradigm in clinical work, one that emphasized data, reproducibility, and quantifiable criteria. This shift toward evidence based evaluation anticipated the core functions of clinical engineering, ensuring that tools not only functioned reliably but also delivered data that could guide critical health decisions. The seeds of the data driven healthcare model were planted here, where measuring the body became as important as treating it. The Second Great Awakening brought a wave of religious revivalism that reshaped American values around personal discipline, social reform, and moral stewardship of the body. Health was no longer seen as merely a physical condition, it was tied to spiritual purity and personal responsibility. This theological framework encouraged believers to care for their bodies as a reflection of their commitment to God, intertwining moral character with physical wellness. As a result, medical oversight and preventive care gained cultural acceptance, not just as clinical interventions, but as spiritually endorsed acts of self care and civic virtue. Religious organizations were instrumental in the founding and funding of many early hospitals, health missions, and charitable clinics throughout the 19th century. These institutions were more than service providers. They were moral projects designed to extend Christian compassion to the sick, the poor, and the marginalized. As churches aligned themselves with the healing professions, they helped legitimize and sustain the infrastructures that would later support the growth of clinical engineering. particularly in their embrace of medical tools, sanitation, and public health outreach as expressions of religious duty. The religious ethos of the era provided a critical culture cover for what might have otherwise been seen as intrusive medical practices. Public health exams, school screenings, and military evaluations, procedures that involved measuring, diagnosing, and sometimes excluding individuals, were morally justified through the language of care, also responsibility and divine stewardship. With this ethical support, institutions could adopt increasingly technical methods of health evaluation without fear of any public backlash. The groundwork was laid for clinical engineering to emerge as a field grounded in both utility and trust. Religious teachings often framed the body as a sacred vessel, a temple to be honored and maintained. This metaphor had profound implications for medicine. If the body was divine property, then it deserved not only protection from harm, but active cultivation and improvement. This perspective helped normalize the use of diagnostic tools and measurements to assess bodily condition. Quantification became not just a scientific practice, but a moral act, transforming health into something observable, something improvable, and worth investing in. Principles that lie at the core of clinical engineering today. In the mid 19th century, physicians began incorporating tools like stethoscopes, tuning forks, test cards, and urine analyzers into routine practice. These instruments were simple by today's standards, but they represented a major shift from a medicine of intuition and observation to one grounded in measurement and physical evidence. This transition foreshadowed the eventual rise of clinical engineering. The use of instruments for diagnostics laid the technical groundwork for the development of systems that would later require professional oversight, calibration, and innovation, roles eventually filled by clinical engineers. Faced with increasing demands from institutions like the military, schools, and insurance companies, 19th century physicians had to adapt rapidly to using these tools not just for treatment, but for objective assessment. The examination of the body became increasingly standardized, and tools were integrated into workflows to increase accuracy and accountability. Physicians were early adopters of what we would now call clinical systems thinking, using instruments to collect data and guide decision making. These adaptations marked the beginning of a more technical model of care, one that clinical engineers would later support and refine. The act of measuring the body, its weight, height, strength, vision, function, was not seen merely as a scientific task. It carried with it a moral dimension, particularly in society shaped by Protestant ethics and public health reform. To measure was to know was to improve. Physicians and public institutions justified the use of diagnostic tools as a way of safeguarding individual welfare and societal productivity. This dual lens, science and morality, helped establish a cultural foundation for the acceptance of technology in patient care and for the professionals who would eventually be tasked with managing it very responsibly. The increase in reliance on tools and quantitative evaluation led to the development of what could be described as the early clinical engineer's mindset. Physicians began to value precision in readings, efficiency in examinations, and reliability in instrumentation. These core principles, so familiar to engineers today, emerged not just from technological necessity, but from ethical imperatives. Inconsistent measurements or unreliable tools could mean misdiagnosis, unjust military disqualifications, or missed signs of disease. Thus, the pursuit of accurate and accountable technology in healthcare was born not only from scientific advancement, but from the deep moral need to protect human well being. The model of structured, instrument based medical examination that began in the military did not remain confined to enlistment procedures. It expanded into public schools where children were assessed for physical development, vision, and hygiene. From there, it entered the industrial workplace where employers sought to minimize downtime and injuries by screening workers for physical fitness. Each institution adopted and normalized the idea that health should be measured, monitored, and recorded, an approach that required standard procedures and reliable tools. This chain of adoption created a lasting infrastructure for health monitoring setting the stage for modern healthcare systems that rely heavily on data, machines, and maintenance. Many of the measurement systems first introduced in the 19th century are still with us. Body mass index, blood pressure, lung capacity, and heart rate remain routine elements of medical evaluations. These metrics, once used to determine battlefield readiness or factory performance, now serve as gatekeepers to insurance coverage, surgical clearance, and school participation. Their persistence speaks to the institutional entrenchment of early diagnostic tools and the belief in quantifiable health. These systems rely not only on clinical insight, but also on technical precision, creating a demand for professionals who can ensure the accuracy and functionality of the tools themselves. As medical technology became more complex and widespread, the need for specialized professionals to support, calibrate, and troubleshoot these tools grew. Clinical engineers emerged to fill this gap, tasked with not just maintaining devices, but also evaluating their effectiveness, integrating them into care environments, and ensuring patient safety. In many ways, clinical engineers are the inheritors of a system first built by necessity for war, for work, for school, but transformed by design. Their role is not simply technical, though. It is institutional, bridging the systems that govern modern health with the human needs those systems are meant to serve. Clinical engineers are often perceived as behind the scenes technical experts quietly ensuring machines work properly, but their role extends far beyond maintenance. They are ethical agents embedded within healthcare systems. Every calibration, risk assessment, or failure analysis they conduct has direct implications for patient safety and well being. Their decisions can mean the difference between a successful diagnosis and a dangerous oversight. As such, clinical engineers operate at the intersection of ethics and technology, where responsibility, accountability, and compassion inform every technical task. They are stewards of trust, ensuring that the technologies clinicians rely on can be used safely and effectively for those in need. The field of clinical engineering emerged from a deeply human centered mission to protect from harm by ensuring that healthcare technology is safe, effective, and accessible. Whether it's guaranteeing that a neonatal incubator is functioning correctly or preventing overexposure from a CT scanner, clinical engineers help uphold the dignity of patients who may be at their most vulnerable. From its inception, the profession has reflected a quiet but powerful ethical stance that no person should be put at risk because of preventable technological failure, and that everyone deserves access to functional, reliable tools that support their care. In modern healthcare, technology is deeply woven into every layer of clinical operations. So, clinical engineers serve as the vital bridge between patient centered care and the complex technical systems that support it. They collaborate with doctors, nurses, IT departments, and administrators to ensure that devices not only work, but work in harmony with clinical workflows and safety protocols. So, this dual awareness of human needs and system performance positions the clinical engineers uniquely. They safeguard not just machines, but the fragile ecosystem of care itself. Their presence ensures that the healthcare environment remains both technologically advanced and ethically grounded. The 1840s were more than a formative decade for the United States. They were a crucible in which the technical, institutional, and moral foundations of modern healthcare were forged. In this era, the first organized medical exams were born out of military necessity, but their impact extended far beyond enlistment. They introduced the idea that health could and should be measured, standardized, and safeguarded using tools and data. The social forces of the time, expansionism, religious revival, and industrialization, created both the need and the justification for new technology enhanced vision of medicine. This moment marked the beginning of a legacy that clinical engineering would later inherit and formalize. The field of clinical engineering didn't appear overnight. It emerged from the convergence of powerful historical forces. National goals like building armies, settling new territories, and industrializing labor required healthy, measurable bodies. Religious movements like the Second Great Awakening cast health as a moral responsibility, reinforcing the legitimacy of public medical intervention. And advancing medical tools made it possible to transform care from observational to technical science. And at this intersection, clinical engineering started taking shape, not merely as a technical discipline, but as a societal necessity grounded in values of protection, accountability, and most importantly, access. Today's clinical engineers work in hospitals, clinics, healthcare systems shaped by this long arc of history. But in an age of automation and rapid innovation, it's easy to lose sight of the ethical origins of their work. Reclaiming these roots means recognizing that clinical engineering has always been about more than machines. It has been about safeguarding lives, preserving dignity, and making advanced care accessible to all. As we look to the future of healthcare technology, remembering the moral vision that launched the profession, this is going to help ensure that progress continues to serve both precision and humanity. Today, clinical engineers face challenges that echo the moral and institutional values established in the 1840s. Issues like equitable access to healthcare technology, device safety in under resourced settings, and the ethical deployment of AI and diagnostics all mirror earlier concerns about justice, stewardship, and trust. Just as the first military exams sought to define and protect the fit body for national service, modern clinical engineers are now tasked with safeguarding digital and physical health infrastructures in an era of rapid innovation and global risk. These challenges aren't new, they are continuations of a legacy where engineering served not just the system, but the individual within it. Modern clinical engineers can draw profound inspiration from their profession's origins by remembering that their work has always been ethically charged. The 19th century physician who picked up a stethoscope to better understand the body wasn't just innovating, he was fulfilling a moral promise. Today, that same promise lives on in every risk assessment, every repaired monitor, and every system brought safely online. By grounding technical decisions in values like dignity, equity, and transparency, clinical engineers can carry forward the spirit of their forebears, not just for maintaining the machines, but preserving the integrity of care itself.